The views expressed on Skeptically Speaking do not necessarily reflect the opinions of the University of Alberta, the Students' Union, or CJSR.
It's a simple equation, really. Take two skeptics, one radio station, divide the evidence, and square the sensibilities. That, my friends, is how you calculate your way into the following hour of programming known as Skeptically Speaking, the show where we ask you to call in and equate everything.
That hurt my head. Thanks, Sean.
Just wait until we get to the real math.
Oh, God. Welcome, everybody. Today on Skeptically Speaking, we'll be speaking about the aforementioned math. And it's actually a heck of a lot more interesting than you may think. But first, we have someone lovely here for our Speaking Up segment. Sibina Fisher, creator of the Phage clothing line. Sibina graduated with a Bachelor of Science with a what's the word I'm looking for?
Specialization.
You know, I need more coffee. In immunology and infection at the University of Alberta in 2007. But she started the line in 2006, combining what she spent most of her time studying, cells and microbes, with art. So welcome, Sabrina.
Thank you for having me.
No problem. So I have to ask, was this a way to procrastinate productively?
I kind of wish it was, but it was more, I did this art festival and I just wanted to do art. So I ended up being like, well, what the heck am I going to do? And everyone does t-shirts, so I was like, cool, I'll try t-shirts. And then I was like, I'll do tattoo-themed stuff because I know nothing about that. That's a good idea. And rethought that one rather quickly. And then I decided, you know what? Actually, bacteriophage look pretty darn cool. My mom went, they're looking kind of scary. Are you sure you want to put that on a t-shirt? And I was like, hell yeah. And I went from there. Yes. Yeah.
So tell us a bit about the images.
So what I use are micrographs taken from scanning electron forgetting the word. It's pretty fabulous. You know, those microscopes.
Things.
Yes, those. And I just look for something that I think is visually appealing and also has kind of a backstory to it that will get people kind of like foot in the door interested in science because, you know, apparently science is scary. And everyone thinks it's daunting and totally way above them or outside their league. But it's not true. It's totally for everyone. It's everywhere. So
the images are of microbes and cells. Like what kind?
I have a bacteriophage, which is a virus, and it preys on bacteria. I've got E. coli, the lovely little guys that live in your gut. And they are helpful, you know, not like the EHEC, which goes around running rampant and you get the red run type thing going on. But anyway, that's really fabulous to talk about. And then I've got like a DNA double helix.
I have the double helix, everybody.
Yes, it was a good choice.
It's
it is
brilliant.
very, very popular. And, you know, neurons, anything you can find in nature or the human body or even multicellular organisms like sea creatures, I kind of found those inspirational. So I went with those too.
Right. Oh, and actually when I initially found Sabina's work, it was at a sort of a local designer show, and I picked up, it was during the swine flu outbreak, and I picked up influenza. It was pretty rad.
Yes. But you didn't even have to suffer the, you know, symptoms.
Actual swine flu?
Yeah.
Yeah, that's cool. I also appreciate that.
Yeah.
So one of the things that I liked about the shirts is that you don't have to be sciencey at all to like these. The images without, if you didn't know what they were, they would look like regular hipster-like designs.
Totally. It's like a Rorschach, you know. You can find what you want in it. And that was the point, because I wanted people to sort of see what kind of design is going on, you know, in this mysterious microscopic world that we don't come across, and how neat everything is. It's really cool. Like, it's amazing. I can't believe these things even exist. When you stop to think about it, it's like, you know, if I had to think about running everything that's going on in my body right now, I think I'd probably just die in a second because I'd forget something really important, like my heart.
I hear that's important.
Yeah.
I don't know, heart or brain?
Yeah, yeah.
One of those.
Well, the brain and the heart hand in hand.
Right. Good point. So what's actually the most popular T-shirt?
I would probably say the DNA double helix, simply because people recognize it. It's, you know, something that's sort of seeped into culture because it's that big, like, image, like, whoa, we discovered DNA. It's what makes us up.
Awesome. So You started with the T-shirts, but now you've expanded to scarves, skirts, and underwear.
Yes. Gotta do the different things. And of course, the underwear is all STD, or if you want to be politically correct, STIs. I don't know, whatever. Who cares, really? But glow-in-the-dark prints on men's and women's underwear. It's pretty fabulous. You can get chlamydia, herpes, trichomonas for the ladies, got to get that parasitic infection in there, an HIV-infected T-cell, and I'm forgetting one, I'm sure.
I would like to point out to everybody that I don't want to say I have chlamydia.
That comes up in all my conversations.
Yeah.
It's like, oh, I've got herpes, chlamydia, HIV.
Yeah, it doesn't have the same ring I was going for.
I own a pair of.
Thank you. Yeah. I should start with that. So what kind of people are actually buying these?
I think people with a good sense of humor. It was meant as a way to sort of break the ice on kind of an important, well, not just kind of, it's really important topic, because we have, essentially, syphilis, right?
Syphilis,
that's the other one.
That was the one.
Syphilis.
You didn't have syphilis in my size.
Oh, no, that's really unfortunate. It's popular. But I mean, we have the North American capital of the world, which is Fort McMurray, in syphilis outbreaks. I mean, it's curable
Really?
with antibiotics, yes.
In Fort McMurray.
Yes.
You heard it here, folks.
Yeah. So, get tested. It's not a shameful thing to have an STD. That's not at all my message, because you know what? It happens. It's a part of life, and the only reason it's upsetting is because it's in the taboo sexual area. Mm-hmm. But get tested, be safe, and make sure that you're treating them instead of, I heard a really sad story about a girl who had to get a hysterectomy because of chlamydia being undiscovered in her. And, that's really sad. And it wasn't her fault at all, It's not like we should be shunning these people. It's something we should talk about and hopefully prevent or treat.
Agreed. And you can help that by wearing pretty chlamydia panties.
And they glow in the dark.
So, where can people see, where can they go to buy these?
I have a website. It's thephage.com, and that's PHAGE, like photograph, not F as in frame. So you can go to that, and I also have an Etsy store, which I just opened up also under the Phage.
Awesome. And I will be wearing the Phage line when I head to TAM in a couple of weeks, so anyone who's attending and wants to see how awesome it looks, come find me. You can't see the panties. Okay.
Privileged people only.
Thanks very much for being here, Sibina.
Thank you so much for having me.
So if anyone out there in audience land wants to appear on Speaking Up, you are welcome and encouraged to send an email and a brief proposal off to feedback@skepticallyspeaking.com. And just so you know, it doesn't matter where you live. As long as you have Skype or a phone line, we can give you a skeptical forum. Again, that's feedback@skepticallyspeaking.com. And please do mention Speaking Up in the subject line. Next, I have a brief announcement. Mike Harrison is the newest member of the Skeptically Speaking team. He's our new media and production coordinator. And what that means is that if it isn't research and interviews, which is my thing, and if it isn't sound editing or website stuff, which is Sean's domain, then it falls under the category of Mike's job. Welcome aboard. So on to Brownie in Motion. Long time no talk?
Yes, it has been a long time. And can I just say I'm very excited that for the next, 45 minutes, we will not be hearing Smooth Criminal or Billie Jean or anything. Not that I don't love them, MJ, but I'm not looking forward to the next week of hearing nothing but MJ all the time.
It crashed Twitter.
Oh, really?
It did.
It doesn't take much to crash Twitter.
Shush.
Twitter
is my
It
friend.
does happen. Okay, I usually get in trouble for this, but I'm going to talk about more than one thing. But only because something really interesting happened to come up today in conversation. So I don't know how many of our audience are out there are interested in cryptids or cryptozoology or any of those weird creatures, chupacabras and all of that sort of thing. But I had one of my coworkers is from Kenya. And he was talking about a story that he'd hear from his grandmother about this particularly bizarre creature that is supposed to be some kind of cat-like beast that apparently has genitalia that, alternatively, depending on which story you get, resembles corn or meat, which is irresistible to chickens. And
Okay, I haven't heard this one.
Just wait for it. It gets better. So this cat-like, weasel-like rodent type thing apparently stalks chickens, turns around, presents its rump, spreads its buttocks, which then apparently become irresistible to the chicken because he thinks it's corn floating attached to the ass of some kind of animal, takes a peck, and then, this is the good part, the creature actually entraps the chicken by slamming shut its butt cheeks and suffocating it with its anus. So
I have no words.
Yes. Well, I have two. Apparently, there are names for this, and so what I'm actually this is a call out to the listeners because I'd really be interested in hearing more of this because it falls into the mythology sort of folklore kind of aspect of stuff, which I do find really interesting. So it's called in Luo, it's called an ogwang, and I was able to find a reference to it by a traveler who was in Rwanda. So apparently in Rwanda, it's called an akiyongwe. And so if any listeners have heard of this thing, this creature, or can direct me to resources, I mean, my Google foo is strong, but I was only able to find one reference to it, at least that wasn't in Rwandese. So that's, yeah, send it in. That would be great. I'd just like to know more about this.
See, he does this when he knows I'm vulnerable.
Vulnerable?
Thank you.
Is that because the chlamydia underwear?
Yes, it is. That is like my kryptonite. Okay.
All right. So the thing that I really was planning to talk about, which was an excellent book that I found one day when we were actually here in the studio working on some stuff, and I thought I'd go take a brief perusal in the University of Alberta bookstore. And so in their sort of general interest, whatever section down in the basement somewhere where they've got stuff that you don't have to be enrolled in a class to buy, I found this book called Stat Spotting, A Field Guide to Identifying Dubious Data. And I thought this fits perfectly in with what we're going to be talking about today, although I know Simon does crazy math that's not so much related to this mundane stuff. But I think it really ties into this concept that science and math need not be so hard, and particularly with statistics, since we're inundated with them, they're everywhere. Understanding them, or at least having some inkling of how they work, is imperative to, I think, functioning in this society. This is a great guide because it's aimed at people that aren't necessarily statisticians, and particularly at the layperson whose understanding of stats is somewhat weak or even non-existent. And what it is it's a guide for how to identify, obviously, identifying dubious data, but how to immediately recognize statistics that might be questionable, and what ways you can sort of train yourself, even without having a grounding in statistical methodology, in understanding what kinds of stats might be a little spurious or something along those lines. So what he does is he talks about He gives great examples of stats that have been reported in the media or sometimes in papers and that, and goes on to talk about why they fall into examples of dubious data or how they could be detected. So he gives out some particular basics. For one is have benchmarks. If you have an idea of the population, birth rates, death rates, particularly in countries, I mean, you don't have to memorize them all. They're easily found. But if you just know, for instance, that the U.S. population is about 300 million, a little bit more than that, and the U.S. all-cause mortality rate, it tends to be about 2.5 million per year. When you hear things like the statistic that he gave, where a website, the author had claimed that 4 million women died annually in the U.S. as a result of spousal or boyfriend abuse. And immediately, well, that's implausible since there's only about 20,000 homicides per year and only 2.5 million deaths in total. It's completely not the case, it's clearly not the case that 8 million women die from this. So, and then goes on, to say it's not necessarily the case in many cases, when you look at how statistics are reported, it's not always the case that somebody is really trying to fudge the numbers, although sometimes that does happen. People try to make interesting, people, especially when they've got a vested interest in whatever disease they happen to be looking at or something like that. I mean, you want to make your stats jump out, grab the public's attention, and, hopefully send you more money for research and that sort of thing. So as he goes on and gives all these examples, he talks about why stats are sometimes incorrectly reported. For instance, sometimes it's just they're just botched. Sometimes journalists put a decimal point in the wrong place. Sometimes the calculations aren't so great. Sometimes you'll hear people will use non-standard units of analysis. They'll report things in ways, particularly you'll see this with health information. They'll report figures that don't conform to the standards of how you report these type of data, which make it really, really hard to compare them against other stuff.
Right.
So when you're not hearing a standard mortality rate or something like that. it makes it particularly difficult. And sometimes it's just individuals, whether they be the journalist or sometimes individuals that have a vested interest in promoting these things, fail to understand the stats that they're actually reporting. So, for instance, there was a fellow with, I think, the British Heart Foundation was talking about the rates for secondhand smoke and the heart disease rates that are resulting from that. And what had happened was regular exposure to secondhand smoke apparently increases your rate of heart disease by 25%. And this guy attributed that to mean that 1 in every 4 people who are exposed regularly to secondhand smoke are going to get heart disease, which is not the case at all. What that means is, of the people that do get heart disease, those who are also, or who are likely to over the course of their lives, those who are also exposed to secondhand smoke are just slightly more. So what that translates into is 4 out of every 100 people develop heart disease throughout their lives. Those that are if we add secondhand smoke into the equation, that only adds up to 1 more individual.
Gotcha.
So it goes from 4 to 5, rather than, as he was saying, a total of 25%. So in that case, he was confusing absolute with relative risk.
So sometimes it's counterintuitive.
And sometimes it is counterintuitive, and I know a lot of people will say that stats are really, really hard to get. That's often the case, and there's that whole intuition aspect around it. But once you've gained a familiarity with it, you're that much better informed and better able to understand these and understand media reports and understand what people are trying to say. So anyways, I highly recommend this book. It's great. Like I said, it's aimed at the people who have no real background in this, and it's a handy-dandy little guide and gives clear and concise examples for each of the cases that he brings up. And then, and goes on to talk about how stats are produced, why they're produced in certain ways, why they're misinformed, and why it's important to know about them and understand them in order to be an effective member of our culture and society.
And what's the book again?
The book, again, is Stat Spotting, A Field Guide to Identifying Dubious Data by Joel Best. And I'll have a link for that up on Brownie in Motion on the website.
Wonderful. Thanks, Brownie.
Thank you. All right, thank you.
So next up is a somewhat esoteric and infinitely fascinating topic, math. So we'll be right back with that after the commercial break.
Here we go.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call in every Friday from 6 to 7 p.m. Mountain Standard Time at 780-492-2577 extension 1. That's 780-492-2577 extension 1. You can also email your questions and comments before or during the show to live@skepticallyspeaking.com, or if you're on Twitter, we're at Skeptical Radio. After the show, continue the conversation on our website at skepticallyspeaking.com, or check out our Facebook group. You can also subscribe to our podcast on iTunes. Skeptically Speaking is also rebroadcast on Public Reality Radio, WPRR 1680 AM in Grand Rapids, Michigan. Citywide LP 99.1 FM in Madison, Wisconsin, and on freethoughtradio.com. And now, back to the show.
And we are back.
Welcome back to Skeptically Speaking. We are here with Simon Rose to talk about math. Simon was born and raised in Grand Prairie, Alberta. He did his 2 years of a music production diploma at the Grand Prairie Regional College before switching into mathematical physics and coming to do his Bachelor of Science at the U of A. He went on to do his master's in math, algebraic topology at the University of British Columbia, and is currently doing his PhD in algebraic geometry. Holy crap. Simon, thanks for being here.
Hi there.
And that, my friend, is a lot of math for us mortals.
Fair amount of math, yeah.
So why did you go from music production to math?
I basically found out that I didn't really like some aspects of the music industry, really. I had to take a course on marketing. I didn't enjoy it very much, and remembered that I actually liked math and physics in high school, so went into that.
Are there any parallels there that we should be aware of?
Some yes and no. I mean, there are mathematical relationships that do show up in music. I mean, loosely speaking, the tuning system that we use, octaves double the frequency, and I think Pythagoras was the first one to note this. There's actually even a little bit more work that's been done lately involving applying very, very fancy mathematical techniques to the study. I don't really know a lot about them. I've kind of skimmed over a few papers about it, but the reason that I studied both is it really was kind of almost a non sequitur.
Gotcha. Well, hopefully what is not a non sequitur is your thesis. But when I asked you about your thesis over email, and I have to read this out loud, you said, the technical description is okay. The technical description is that I'm studying Gromov-Witten theory of orbifolds, which isn't very helpful, I admit. More loosely, the idea is to study the structure of some thing, an orbifold, which is something that is almost smooth but might have edges or pokey bits or corners, by studying all the different types of surfaces that you can fit into it. Loosely speaking. It's complicated. So that, Simon, is when I started to get scared about this show. So please tell us about your thesis, possibly using only small words.
Okay. Well, again, I'll just restate the description there. It is the Gromov-Witten theory of orbifolds. Gromov and Witten are just a pair of mathematicians who happen to have their name put on this, so that part's pretty easy to understand. Now, Gromov-Witten theory, when it comes down to it, it's about counting things. It sounds kind of silly when people talk about mathematicians and don't really know a lot about them. People ask sometimes, do you just count to higher numbers or do you just compute harder integrals? And sometimes, yes, actually. Counting in this case, it's not that I'm trying to count to 57 or something like that.
You're frustrated. Okay. Explaining to mortals must be difficult.
It's a little bit weird to explain because there's a lot of technical things going on. Any sort of description I try and provide starts to lose a lot of those details and get a little bit fuzzy. I mean, the email description there, just even explaining what an orbifold is a little bit awkward. I mean, if you know what a manifold is already, and not something that's in a car,
that's the only one I know.
Not just referring to lots of things. If you know what a manifold is in the mathematical sense, then an orbifold is actually a fairly easy thing to understand. The problem is most people don't know what a manifold is in the mathematical sense. I can kind of explain that one, though.
Okay.
So, a manifold, the idea is that everyone knows a little bit, hopefully, of Euclidean geometry. At least they've heard the idea of plane geometry. So you're talking about circles and triangles and straight lines and parallel and so on and so forth. So the idea is that if you want to take a whole bunch of flat things like a plane and you sort of glue them together in such a way as to create something that's not a plane, but, around any given point it kind of looks like it. The surface of a sphere is a very good example. If you look at, for so long we thought the Earth was flat. And it's because at any given point on the Earth, it looks pretty flat. Mm-hmm. And that's essentially, in a sense, you could say that that's just because the surface of the Earth is in fact a two-dimensional manifold. 2 dimensions in that there's 2 independent directions on which you can walk, or in which you can walk. So that's kind of a manifold. You, of course, can have 3-dimensional and 4-dimensional and 18-dimensional manifolds if you want. Now, the study of those, of course, is a very, very exciting part of mathematics and pretty much has been for quite a long time. But orbifolds, on the other hand, they're like manifolds, except, as I said in the email, instead of everything looking nice and flat and smooth locally, at some parts of it you might have corners or you might have
a bump of some kind. Okay.
That's a loose description of what orbifolds are.
Okay. I feel like I'm forcing you to explain things to chimpanzees, and it actually hurts me. So I'm going to ask you an easier question, hopefully. Okay. So what does it mean that math is the only universal language? I keep hearing this.
So, math is universal language. I think that the way I would interpret that statement, because you do hear it a fair amount, is just that if you take any person out there that wants to just start studying the world around them, not necessarily just a person on Earth, but conceivably a person anywhere else in the universe, if they just sit down one day and say, I want to study why things are the way they are. They want to study why a ball falls in a certain way. They want to study why planets orbit around suns and suns orbit around centers of galaxies and stuff like that. It would be hard to do that without developing some sort of mathematics.
Right.
People obviously in a different galaxy might not really describe it the same way we do. I mean, different cultures on Earth develop different approaches to mathematics throughout history. But I would assume that there would be something in common in the way that you're modeling complicated physical phenomena with structures that sort of abstract away these things. And one could hope that, as a consequence, if we were to ever meet a foreign culture from somewhere very far away, that this would perhaps provide a stepping stone in terms of being able to communicate with a completely alien species. The book Sphere by Michael Crichton actually had a little bit of this in there. Developed a plan for what would happen if an alien encounter ever occurred on Earth, and one of the people they made sure they had in that group was a mathematician. I don't know if you think Michael Crichton is necessarily a realistic author, but the idea is a good one.
He brings up some interesting concepts, and that's sort of actually, speaking of concepts, okay, so let's use your, aliens came to Earth. So they use a different language, they have different symbols, they possibly have higher intelligence. What if they don't think in the same way? Could we still communicate using math? Are formulas something that are universal across the way we conceptualize things?
It's not really the formulas. In all honesty, this would be a hard thing regardless when you're running into a completely foreign culture, is figuring out how exactly you would start the communication, I guess. I am not really someone who studies how the communication between different cultures works, but the hope would be that somewhere in this we would be able to find a way to describe the same phenomena, talking about planets orbiting around things, and certain fundamental parts of nature, the speed of light, the fine structure constant, all these sort of physical things that somehow or other we might be able to use these to start communicating with alien species. Actually, again, speaking in fiction, the book and the movie Contact actually both had this in that.
Okay. Well, now another question. What does it mean that math is the only pure field? And the reason why I ask this is, and I emailed this to you, audience. I don't know if you've seen that XKCD comic, the Fields Arranged by Purity one. For those that don't know, XKCD is a webcomic about science, tech, math, and relationships, actually, and it's hilarious. And really, the only things that I really understand about math, I learned from XKCD.
That's not a bad start.
Thank you. And the forums, actually, they're wonderfully helpful. So the comic I'm talking about is just basically, it has scientists pretty much slagging each other as to which field is the most pure. Like psychology is just applied biology, biology is just applied chemistry, chemistry is just applied physics, and math is simply math. But you know what? The funny part of that is really lost in translation. So the first person, audience, to email live@skepticallyspeaking.com with a link to that specific XKCD comic so that I can post it later on the blog and I don't have to find it. Thank you. Because I want to show you the funny. You will win a Science-y prize. I have prizes. So that's live@skepticallyspeaking.com. And so, Simon, explain why math is a pure science.
It's pure in the sense that, if you look at the XKCD picture there, you have the ones I'll pick the most where I can really have some better understanding is talking about, say, biology being applied chemistry or chemistry being applied physics. My understanding of chemistry, when you're talking about, molecules and atoms interacting, what chemists do, they look at higher level structures coming from physics and do their own little thing with it. But really, at its fundamental building blocks, chemistry is really just physics. I'm sure chemists in the audience might disagree with this to some degree. But really, you start with physics and you kind of work your way up and you end up getting into chemistry. In chemistry, you work your way up through bigger and bigger structures and you get your way to biology and so on and so forth. And as for math being the purest of the pure, the peak of this ivory tower, I guess, well, physics really is, in a lot of ways, applied mathematics. If you look at what physicists do, and it seems to, in my experience, it's even more true nowadays than it might have been in the past, where what physicists study is remarkably abstract mathematics, but what they're doing is they're using these very, very complicated ideas to try and model physical phenomena, to somehow understand the physical world better. And mathematics doesn't really, okay, it arguably doesn't really have anything to that. I would make a slight argument that mathematics is applied logic, but that is probably debatable.
Okay, well, what does that mean?
Well, I mean, what mathematicians really study is we study what you can do with logic. We study, if you start with a certain set of rules, axioms, or whatever you want to call them, we sort of study what conclusions can you draw from these set of axioms and rules of inference. So basically, we're just applying logic, that we're applying the formal rules of logic to study certain abstract objects.
Okay.
So, I mean, that in that sense, I would say that the math is applied logic.
Okay. So, okay, I hear that math is the only thing that can be certain and empirical. Is that correct?
That's an odd, in a sense, yes. Certain, I will go for. As long as mathematicians are being careful, which sometimes we're not, as long as mathematicians are careful, I would say that everything we do, in that, again, as I was saying just a moment ago, if you start with a certain set of postulates, a certain set of axioms, and if you're careful with what sort of rules of inference you play with these, then it's absolutely certain that something that satisfies these conditions will necessarily also have these properties here that we find interesting. Whereas every other science out there, there's some fuzziness that's just inherent in what it is you're doing. I mean, in physics, for example, we just can't know everything that's going on in a system. I mean, even ignoring things like quantum uncertainty, the three-body problem is a classic thing in physics, where if you have three things trying to orbit one another in some way, except in certain special cases, we just can't properly model it. Math can be certain. Physics and so on and so forth, and everything else past there, it just necessarily loses some of that. It's not a flaw in these things, it's just the nature of the beast.
Okay, so callers, we know you're out there. Phone 780-492-2577, extension 1, or you can send an email to live@skepticallyspeaking.com or on Twitter @Skeptical Radio.
And we already have a winner for our XKCD comic.
Thank you.
Yes, it's comic number 435. And bonus prize to not the same person who finds the one with the ballroom.
Just for fun?
I just love the ballroom. Spherical, geographical shapes, all that good stuff.
Really? You're going to go there?
We've talked about building a ballroom. Don't pretend like we haven't.
I know. We really have. And actually, we almost started costing it out. So
you did find a calculator.
We did. So, again, 492-2577, extension 1. And I believe we have a caller?
Yes.
Hello, Nathan.
Here. Yes. A quick question here. I've heard it said that the concept of zero is key to higher math. Now, I've never actually seen where, but I was hoping you might be able to elaborate on that.
That's actually a really good question. The concept of zero, I mean, it's a strangely relatively new thing in the history of mathematics, to my understanding. As for it being a key to higher math, everything algebraic that pretty much necessarily. So I'm going to take a step back here for a moment and say an algebraic object in mathematics is just something where there's rules for how to combine elements, like maybe adding things or maybe multiplying things together. Now, where zero comes in is a really nice property for any algebraic object to have is you want to have something so that we want to have what's called an identity element, where if you combine any object with this special thing called the identity, that you get the original object back. And 0 is such an object when you think about addition. 0 plus 17 is 17. 0 plus 5.2 is 5.2. So 0 is an identity. So, well, I guess I would say it's important to study sort of any algebraic thing is that if you want to be doing any sort of fancy schmancy algebra, you do need to have a notion of 0. But historically, I mean, abstract algebra, where you study these algebraic objects, is really only about 150 odd years old, so we maybe didn't realize we needed it until recently.
Okay. All right. Thanks.
Actually, on the number 0, actually. So is 0 a real number, or is it just a placeholder?
Okay, just when you say real number, I assume you mean real in the colloquial sense?
Yes.
Okay, just making sure, because real number has a technical meaning.
Yes.
I'd say it's a real number, as real as any other number. I mean, when it comes down to what most mathematicians consider numbers, any number is pretty much... I'm going to hedge here a little bit, but I'm just going to say that every number is kind of the same as any other number. There's differences from one to another. I mean, there's obviously the irrational numbers and the rational numbers and so on and so forth. 0 is very definitely a rational number. It's an integer and so on and so forth. But it's a number like any other. I mean, when I the way I say that it's kind of the same as any other is when I picture numbers, I really think of them as lying in a line, and any point on that line in that sense isn't really different from any other point.
Okay, that actually made sense to me. All right. And actually, what we're going to do right now is go to an ad, and then we'll come back and read some emails.
Okay.
Next time on Skeptically Speaking, we'll be discussing storm chasing with Jeff Richardson, the creator of the website Tornado Quest. So, is storm chasing anything like the movie Twister? How do lightning storms, tornadoes, and tsunamis work? And how likely is it that some kind of severe weather condition will kill you? And is meteorology the only field where it seems like you can get away with being wrong 50% of the time? All this and more on the next Skeptically Speaking, every Friday at 6 p.m. Mountain Daylight Time, here on CJSR.
And we are back. All right.
Hello, everyone. We are back talking about math with Simon Rose, and we have some emails.
All right, let's jump right onto them there. As my screen goes black, that's what I get for not plugging it in. All right, we have, how is it that Fermat's last theorem, theorized in 1637, has not been proven yet? So
Fermat's last theorem, it actually was proven in 1994.
Well, there you go.
It was actually a very big deal. Andrew Wiles is the guy who proved it, and he proved it using some incredibly fancy mathematics that certainly would not have fit in the margin of whatever Fermat was writing in. But I don't think that Fermat probably had the same ideas when he was thinking about his clever little proof. There's actually a very good book written about this by Simon Singh called Fermat's Enigma. It's the small little paperback book, and it actually has a really pleasant overview of a lot of the mathematics involved, and it's for a fairly friendly level of mathematical reader too.
Okay, cool. Well, emailer, I hope that answered your question. We have another email here.
Okay.
Arjun writes, I like your talk show and got to know it through Twitter. I'm a physicist and mainly interested in foundational issues, also about mathematics. Math is an extremely useful tool for physicists. It helps to formulate physical quantities and variational laws with numbers and differential equations. However, on some aspects, there seems to be a gap between the mathematics and physics. Example, in mathematics, some numbers are irrational or transcendental, square root of 2, pi, while they express rationally defined physical quantities. How does it come that in math, pi is transcendental/irrational, while in physics it can be defined as a ratio of two quantities? For example, pi is the ratio between the length of the path along the circle and the length along its diameter. So it is rationally defined as a real physical length, the perimeter of a circle. If pi is transcendental/irrational, the number 1 should also be a transcendental/irrational, because changing units can make the perimeter of the circle unity and make the length of the diameter 1/pi. This problem seems to be related to a general question, what makes a number? So Simon, can you first translate that question and then answer it?
Yes, I can.
Thank you.
So the question is, okay, I can actually answer the question relatively quickly. But the question is about what are called rational numbers. There's a lot of different types of numbers that all kind of fit into this line I was trying to describe earlier. There's the integers like 1, 2, 3, 4, 5, -1, -18, and so on and so forth. So those are the integers, including 0. There's the rational numbers, and now the rational numbers are ratios of integers, hence the word rational. So 1/2 is a rational number. 6/3, that's a poor choice, that's 2. But so 6/5 is a rational number. 17/29 is a rational number. 1 is also a rational number because it's 1/1. Now, there's also things that are irrational numbers. These are any number that cannot be represented like that. Now, square root of 2 is one of these. If you draw a little triangle where a right-angled triangle with the two right-angled sides of length 1, then the diagonal is length square root of 2, and you can use this to show that it actually has to be an irrational number. And then there's transcendental numbers, and that's kind of a messier can of worms. Now, the question as to whether or not we should describe pi as a rational number or an irrational number can be answered pretty quickly here in that when a mathematician is speaking of a rational number, they're really specifically referring to a number that can be described as the ratio of two whole numbers. And pi cannot be described in that sense. I mean, it is, as the email says, it is a ratio of quantities. I mean, it's true in mathematics as well as in physics that we describe pi as the ratio of the circumference to the diameter of a circle. But that ratio is not a ratio of whole numbers. It's just a ratio of two different quantities. So hopefully that answers that.
All right. And sorry, we can't follow up with the emailers. It's too bad about that.
Yeah.
Okay, so I want to know about pi. Because I was out of town this year on March 14th, which is Pi Day. So why is pi cool enough to have its own day?
Part of the thing with pi is, compared to a lot of the other fancy mathematical constants that exist out there, is that everyone can kind of understand by just drawing a picture what pi is. I mean, if you draw a circle and you stick a ruler across it and maybe use some string to figure out what its perimeter should be, you know what? Someone in first grade can do this, and they can do a little bit of an experiment. They can tell that pi is slightly larger than 3, less than 4. And, if they have long pieces of string and they're very careful, they can maybe get a better approximation. And I think that might be part of why it's a number that sort of grabs everyone's attention. It's, it's got its own special symbol for it too, which is very pretty. But again, it's an easy one to explain, whereas if you look at a lot of the other mathematical constants that exist out there, I mean, ones mathematicians would think are very, very commonplace, like E, the base of the natural logarithm is a good one. The Euler-Mascheroni constant, gamma, is another kind of neat one. All these different numbers here, it's harder to explain to people how they arise and what their purpose is. But pi, I mean, look at a manhole cover, look at a plate, that's pi. Or look at a pie, that's pi.
But pi is also, it's treated as a bit mystical, is it not? Maybe not mystical, but it's as a signifier of greatness. in a way, because, for example, I've heard quite a bit about Egyptians using pi and how it signifies, them being technologically advanced.
That, I have to admit, I can't really say a lot of. I don't know much about the history of that. In email earlier, you'd sent me a link to it, and what the link seemed to suggest is that if you look at the ratio of certain sides of a pyramid to its height or something like that, that it's close to pi. But what the article, as I recall, was saying is that it's sort of close to pi, but not really that
But
close.
not really pi. Right.
And I mean, it's one of those things that people are very good at finding patterns. This can be to our downfall at times. And if two things look kind of close, we might ascribe more significance to it than maybe you should be ascribed. And it's entirely possible they were trying to encode the value of pi into the height of their pyramid. But it's also possible they just decided that, hey, let's make a pyramid this tall, and it happens that it kind of ends up being sort of close to pi.
Well,
I mean, I don't really know, so...
Well, it's interesting because the Egyptians aren't the only ones who this has been ascribed to. It's actually in religion and their use of numerology, which is interesting. There was an article that I was looking at before the show, and it was basically trying to convince the reader that that the Hebrews were every bit as good as at pi as the Babylonians or the Egyptians. Because there was some slagging of the Egyptians' much better pi approximations than when the Hebrew Bible was written.
Yeah. That article there, I kind of looked over it, and I have to hesitate here too because I'm not a studier. I'm not a student of Hebrew, but there's a degree to which it kind of struck me as a little bit convenient, the way things are set up. In the end, as I recall, their argument went that there's a portion in the Talmud, I believe it is, where they're describing the size of something being built, and they talked about how the length of the diameter was 3 cubits and 10 cubits around or something like that. And it's clearly not a very good approximation of pi, but apparently the way it's written down uses a certain pair or a triple of Hebrew characters, but the way you would say it uses it differently. And so what the person did, who's talking about this, is that they compared the numerical value of these Hebrew characters one to the other and formed a ratio out of it, and it turned out that 3 times this ratio was a very good approximation to pi. Now, where I find myself a little skeptical of this is that why did they use the ratios the way they did? Why didn't they do 1 over that ratio instead? I mean, it sort of rings that they might have. It looks like someone could have just been fiddling with things and said, hey, this is pretty close to pi. And it is a very good approximation, but it comes across more as numerology and just kind of playing around with numbers until the numbers look the way you want them to, as opposed to necessarily having other meaning. Maybe it was there, but the article, as I read it, did not in any way convince me of that.
No, and that's the impression I got.
Well, speaking of imaginary numbers, why do we need them? That's our next email question, actually.
Now, okay, there's a couple of reasons why you could say we need imaginary numbers. If you read Calvin and Hobbes, it's because we want to be able to do addition in general, but that's not usually why mathematicians use them. And 11t3 is not an imaginary number. Anyways, they come up in a couple different places. Physicists need them, because when you talk about, if you try and describe things in quantum mechanics and you're talking about wave functions, Schrodinger's wave equation is actually a complex equation. It does involve imaginary numbers in it. And it works out that way. That is what we end up using to describe the propagation of quantum waves. So physicists need them, certainly. Electrical engineers use them apparently as a convenient way to do certain computations, though I know actually very little about that. But as for why mathematicians might be interested in them, there's a thing called, the real numbers, which we usually draw as a straight line, and as I was describing earlier, they have a problem. It's not a very big problem, and it does depend on who you ask whether this is really a problem. But, so, if you think of a polynomial equation, so a polynomial equation is something that looks like, x squared minus 2 plus x or something like that, just involving powers of x and so on and so forth. Now, if we want to find where a polynomial equation is 0, hopefully most people do recall in 10th grade, give or take, where we learned the quadratic formula. And this is a formula you could use. You'd throw in the coefficients and it would spit out where this thing was 0. Now, the problem being that not every polynomial equation, if you pick your coefficients to be real numbers, has a 0 somewhere. If you look at the polynomial equation x squared plus 1, there's no real number that makes that 0. The problem is that any real number, when you square it, gives you a positive number. A positive number plus 1 is also a positive number, so it can never be 0. So this is, for various technical reasons, this is not a good thing. And so one reason you might want to study complex numbers and why you might want to have these imaginary numbers kicking around is because you want to fix that problem. You want to make sure that if I give you any polynomial equation whatsoever with real numbers as its coefficients, as its little labels for the powers of x, that you should be able to find a root of it, a 0 of this equation. And if you look at the complex numbers, you get that. And they're what's called algebraically closed as a consequence. And that's very, very nice. And it turns out that actually what I study, algebraic geometry, basically it's a lot nicer if you have things that are algebraically closed.
Just wanted to remind our callers, you have some time to still sneak in a question, 780-492-2577, extension 1.
So on to chaos theory. What is it?
So chaos theory, it actually is one of those domains in math where I actually don't really know a lot about it. I probably don't necessarily know much more than anyone who's seen the movie Jurassic Park knows. Where chaos theory comes in is if you want to study any sort of phenomena the kind of the catchphrase, as I understand it, is sensitive dependence on initial conditions. And what this means is that if you just perturb the initial setup of whatever you're doing just a little bit, that things could end up drastically different a long time down the road, or maybe even not so long down the road. Now, why this is important is that ideally, when you're modeling physical phenomena, and any sort of phenomena, what you want to do is if you have a total knowledge of the system at a given point, that this should allow you to predict its evolution from there on until eternity. Okay, that's all well and good. However, finding a total knowledge of the system is essentially impossible.
Okay.
Even in terms of ignoring things like quantum, even just thinking classically, it's just there's so much information to know. So your hope is that, well, maybe we can only find out a little bit of the information and it'll be good enough. Now, the problem is that most of the time, for any sort of classical system, this is okay to some degree. I mean, if you don't know, if you're just off by a little bit in your approximations or your lack of knowledge, it doesn't make a huge difference down the road. These kind of all come out in the wash. But a system that is chaotic, that's not true. If you're off just by a little bit, the system really, really quickly starts behaving incredibly differently depending on what you started with. And it's harder to predict these systems. I mean, in very short time scales, you're okay, but anything longer than that, it starts going crazy. Weather being the classic example. I mean, if we knew the position of every single molecule of oxygen and nitrogen and everything in the air at a given particular instant in time and where they were moving and everything, you could hope that we could then describe weather on Earth perfectly.
Well, speaking of weather, we're actually going to be delving to the exact topic next week, but we do have a phone call here. We're going to try to sneak it in before we run out of time.
Yeah, sure.
Hello, caller.
Hi. Would you say that the foundation of mathematics is counting?
Maybe. I'd hedge on that. Actually, foundational mathematics, nowadays I would actually really say it's physics and the study of the natural world. I mean, most of mathematics from the 1600s on, to the best of my knowledge, really comes from studying physics.
Right. Does that answer your question, or I guess the caller must be on there. Oh.
All right. Okay. I guess what I want to know about chaos theory is, so is this a mathematical concept, or is it really physically possible that a butterfly could flap its wings in Texas and cause a tornado in Toronto or whatever?
It's a really good catchphrase, but to the best of my knowledge, it is actually true as well. It seems kind of silly and counterintuitive. You'd expect that a butterfly flapping its wings would really, however much it moved some air, it should come out and, it should just kind of dampen out, 3 feet away. But again, weather is one of those systems that is very, very dependent on changing your initial conditions just a little bit. And a butterfly flapping its wings versus not flapping its wings are different initial conditions. And it might not be that butterfly flapping its wings in Texas today causes hurricanes hitting Toronto 5 minutes later. But what it more means is that if you look at some point in the future, I don't know exactly when that would be for a butterfly flapping its wings, if a butterfly had flapped its wings, maybe 3 weeks later the weather's sunny versus maybe 3 weeks later it's rainy. And of course, all we can see is that it was rainy or it was sunny, and we're not really going to know the difference one way or the other. But the point is that that butterfly may have had a large effect, even though we can't really know one way or the other what that effect was. It sounds kind of silly when I describe it that way, but I mean, to the best of my understanding, it is actually a legitimate statement.
I think it's just the exponential compound of events over time. Just unpredictable. But we are actually getting right to the end of the hour here. I think Des has a few last things to cover here.
Yeah.
Well, I actually was going to say I think we're out of time, folks. So I actually don't know if this cleared anything up for any of you guys.
We hope it helped everyone.
But my brain hurts. So thanks so much to Simon Rose for being our guest today, and to Brownian for his work before on stats. I've completely had my brain wiped in the last, honestly, 40 minutes. My brain's been wiped.
I'm glad we could help.
Thank you. And thanks to all the listeners, and thanks to the people who called and emailed in. And we will see you next week on Skeptically Speaking.
See you again, everyone.
Cheers.
Exist. The moon is painted on things sometimes fall up, but you never see. And everything you believe is a lie.
Dinosaurs were invented by God as a test. Our bodies don't rot when we die. The hippies are working for the government. And everything you believe is a lie.
Lie, la, lie.
Lie, la, lie, lie. Lie, lie. Everything you believe is a lie. They're wee tiny dwarfs inside your TV.
And nobody cares when you cry.
Your mother resents you. She wanted a girl.